Good afternoon, everyone, and welcome to another session of Science Chronicles. We hope you're as excited for today's session as we are. This webinar is organized by EcoSF in collaboration with IPKI. For those of you who are new here, the EcoScience Foundation is a specialized agency of the Economic Cooperation Organization, an intergovernmental entity with 10 member states, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyzstan, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan. Its mandate is to promote science, technology, and innovation among the ECO member countries. IPKI is an organization committed to making the world a better place by promoting science education, fostering intellectual curiosity, and bridging gaps in access to quality learning opportunities. Today's session takes us on a fascinating journey through one of the oldest and most inspiring pursuits in human history, the quest to see the universe more clearly. From Galileo's first observations through a telescope to today's state of the art astronomical instruments, this talk will explore how our ability to capture sharp images of the cosmos has evolved and how these advances have transformed our understanding of the universe. We are deeply honored to have with us Professor Pierre Léna, a distinguished French astrophysicist and emeritus professor at the Paris Observatory and the University of Paris. Professor Léna has been at the forefront of modern astronomy, contributing significantly to the development of infrared imaging and playing a key role in the design of the European Very Large Telescope in Chile. Beyond his groundbreaking scientific contributions, Professor Léna is equally passionate about science education. In 1955, he co founded the Hands on Science Inquiry Initiative, a movement that transforms science teaching in schools by promoting hands on inquiry based learning. Through this foundation, he has worked with educators and institutions around the world, including in Pakistan, to inspire curiosity and critical thinking in young minds. Please join me in warmly welcoming Professor Léna. Professor Léna, the floor is yours.
Oh, thank you very much. Well, it's a pleasure to be with you this morning, and I thank warmly the EcoScience Foundation, its president, and also my friend and former president, Manzoor Shumro. The topic I'm going to develop for you this morning is one of the most fascinating of today's astronomy. It's related to instruments and to the ability of those instruments to make sharp images with a lot of details. And of course, the more details we have, the more we know. Think of the moon. Galileo, with his small refractor, was able to see mountains that nobody had seen before. Why is that? And which progress are we making today? Well, to understand that, let's see, I need the next slide. Oh, to understand that, let's first have a look at our human eye. In fact, it's a remarkable instrument already. You have a cross-section of it. The naked eye, you see it has a lens, so it's a small refractor in a sense. On the background of the lens, there is the retina, where the image of the landscape or the sky is formed. This retina has cells, which are called cones or rods, bâtonnets in French, which have a finite size, a few microns. And because of this finite size, the limit of the details that the eye can see are not infinitely small. If you look at the scale at the bottom of the image here, you see that the limit of the eye is 5 to 10 minutes. What are 10 minutes? Well, if you look at the moon in the sky, it has 30 minutes diameter. So 10 minutes, which is an average human eye capability to see details, give you the possibility that all of us have experienced to see some details on the surface of the moon, what we call the seas. In fact, those dark areas are not seas, but we see those details. But we don't see very small details. We don't see the craters. And if we take binocular immediately, this resolving power or ability to see details is better. Tycho Brahe, using the eye again, with but very smart way to use it with alignment instrument in the 17th century did about 10 times better, 1 minute. But that was the absolute limit until Galileo, 1610, who suddenly jumped to 10 arc seconds, so a factor of 6. And then we had to wait until the slow progress of telescopes, I will speak about that, to reach in the 1980s 1 arc second. And there was a fundamental limit, which I will comment. So nothing seemed possible. But suddenly, a new jump came with the modern optical telescope, and we go to 20 milli-arc second, or even much better. And I will also show you that. Now, on the right, you have the night sky, and in Pakistan, you can also see the Pleiades, this small group of stars. Now, it's a good test of the sharpness of our visual acuity, because if we look at the stars with if we look at the stars with the eye, we see a fuzzy cluster, and that's the limit of 10 arc minute of the eye. Of course, if we take a photograph with a good instrument, then we see all the details. So going from the limit of the eye to the much better details was the challenge I'm going to describe. So let's look at the first stage of that. From Galileo to Newton, Newton about 1680 to the years 1980, 40 or 50 years ago. Then we had a fundamental limit, which astronomers call the saying, if you look at the image of a star given by any telescope, as soon as the size of the telescope is more than a few centimeters, you see this image broken in pieces instead of having a sharp point of the star image. And now the movie is not starting. So what happens? Everything seems blocked. It was, here it is. So you see how the image looks. And this size, which is sort of a random size, is about 1 arc second. Of course, if you are on the top of a mountain, it's much better, maybe half of that, not so much better, but on the average, it's 1 arc second. And this is due to the atmospheric turbulence, the fact that the light has to cross the atmosphere and becomes deformed. And this deformation is an absolute limit. Isaac Newton described that very well. When we look upon the stars, there is a perpetual tremor. The rays of light, all these illuminated points constitute one broad lucid point composed of those many trembling points, what you just saw, confusedly and insensibly mixed with one another by very short and swift tremors. And today we know that those short tremors are on the order of a fraction of a second, maybe a 50th of a second. And thereby, and that's the important sentence, cause the star to appear broader than it is and without any trembling of the wall. Of course, if you take a photograph, this trembling will just average out and you will get a fuzzy image. Here on the top, you can see 3 exposures. So it changes in time. Each exposure is separated by about 1 second. So the pattern is like that, and you have lost the beautiful image on the right that the telescope should give to you. It should be limited, of course, by diffraction. So there is a finite size in the middle, but the size of this image is very small. Lambda is the wavelength of the light. D is the diameter of the telescope. And if, for instance, you put numbers, we'll do that in a minute, you see that this is much smaller than this big spot of 1 arcsecond. Astronomers call that the saying. So this was an absolute limit for telescopes larger than a few centimeters for centuries. Then in 1970, a French astronomer, Antoine Laberry, discovered that, in fact, you have details in this image. In other words, the information through when the light crossed the Earth's atmosphere, the information on the star size is not entirely lost. An illustration of that, which is from the original observation of Laberry made at the 5-meter telescope on Mount Palomar in the United States. When he looks at the star, which is a point star, then you have this figure on the left. And when you look at a star which has a finite diameter, and you see here the star Betelgeuse Alpha Orionis is 50 milliarcseconds, so it's 20 times smaller than 1 arcsecond, and you have details there. So Laberry understood that the information was not entirely lost. Therefore, there was a possibility maybe to recover the sharpness of the image. That was his conclusion, and we'll see what the next step is. But before that, and because it has become so critical in the last 40 years, I will tell you a little bit about the story of the black holes. Initially, it was the idea of dark stars, and this idea was raised very early, actually, in 18th century, independently by a British person, John Mitchell, and by a French scientist, Pierre Simon de Laplace. And their idea was summarized in the text which is below. Think of a big body, which is very massive and still not too big, and then maybe the light submitted to gravitation, that was the idea of the time of Newton, could not escape this body. Exactly like on the right, when we have a stone launched from the Earth or a satellite or a rocket, then if we give enough energy, then it will leave, but if the energy is not sufficient, then the stone will stay around the Earth or the satellite. That's exactly the way we put a satellite in orbit. And this drawing is adapted, but it's exactly the drawing of Isaac Newton. We understood that this escape velocity is simply given by a simple formula. The projectile can escape when its kinetic energy is equal to its gravitational energy. And the gravitational energy, of course, depends on the radius of the Earth, the mass of the Earth, the mass of the object, which is also the mass which is in the kinetic energy. Therefore, you can solve the equation which gives you escape velocity which only depends on the gravitational constant, the mass of the Earth, and the radius of the Earth. So the idea is simply if the escape velocity computed by this formula is larger than the speed of light, which was known at the time of those two persons, then light cannot escape. There should be dark stars. Of course, this was completely revolutionary of the time. Nobody had ways, but at least the idea was there. So the next step was general relativity, 1916. I should have the next slide. very slow. I cannot have the next line. Here it is. Well, general relativity elaborated, of course, on the idea of space-time configuration. Some of you listeners know about it. And Einstein said that the following: general relativity implies that if a mass of matter is in a sphere is contained in a small enough sphere of radius, which is called the Schwarzschild radius, which expression is very simple. Here you have the expression. It only depends on the velocity of light, of course, of the mass of the object, and of the gravitational constant. For instance, if you compute this radius for the Sun, you find 3 kilometers. This means that if you concentrate the mass of the Sun in a sphere less than 3 kilometers, light cannot escape. If you do the same thing with the mass of the Earth, this is 1 centimeter. So this idea was very central, and astronomers were doubtful of that could really exist in nature. You have this quotation from Eddington, the famous astronomer Arthur Eddington, who said, "I think there must be some law of nature that prevents a star from behaving in such an absurd way." But at the same time, 1939, the young Robert Oppenheimer, who later worked on the atomic bomb, of course, everybody knows that, questioned what happened to stars. Because if a star is larger than about 1.5 solar masses, then it falls on itself. And then how long will it fall on itself? The question at that time was unanswered. But of course, it was something like the idea of the black hole. So, question about black holes was in the air, should I say, until the 60s. But in the 60s, the proof that black hole exists in the universe was given. And this is my next slide. It takes time to come each time. How was that proof given? It was given in 2 different configurations. One configuration was given in double stars. I don't know why it's so slow in switching from slides. Here it is. Okay, it's just slow because it's slow. Okay, so the proof was a twofold proof. In 1963, a double system of stars, you have one revolving one around the other, was observed in X-rays. One had the first rockets carrying X-ray telescopes. And it was found that it was a very powerful X-ray sources. How could that radiate? And finally, it was understood that this was a black hole. One of the 2 objects, which was not visible with the eye or with a telescope, so it was not emitting a normal light, but the surrounding of it was swallowing matter from the other star, and this matter being accelerated was providing the X-ray radiation. And the object responsible for that was absolutely invisible, but one could compute its mass with simple Kepler's law in a double stellar system, and it turned out to be the first black hole. So this was 1963, And since then, 60 years, it has become a very, black holes have become subject of fantastic studies. The second case was found a year later. A quasar, a very distant galaxy, 3C273, was observed to be extremely bright, much too bright than a normal galaxy would be with just the light of its stars. And this object was so distant that you couldn't see the light of the stars. So there should be in this object another source of radiation. It was a black hole accreting the matter from around it and again radiating a lot of energy. In both cases, the black hole makes a conversion of gravitational energy, falling matter, into light, radiative energy. Let's not talk about gravity waves, which would be another subject, not so simple. So finally, the black hole were present in galaxies, like in true C273, in many galaxies. Today, hundreds of galaxies are known to have very massive black holes, million to billion solar masses. What about our galaxy? It was the work of a remarkable German astronomer, Reinhard Genzel, who obtained the Nobel Prize in Physics in 1920 for his discovery that there was at the center of our galaxy a black hole. And he could even measure the mass of this black hole. And again, it's slow, but I hope you have it in front of you in a minute. Here it is. So you have the picture of Reinhard Genzel. In the back is the European telescope. We'll talk on it. And at the center of our galaxy, here's the Milky Way at Cerro Paranal in Chile. So the center is around here. There is a black hole, which is 4 million times the mass of the Sun. And the Schwarzschild radius is about 40 seconds of light. And seen from the Earth, and remember this number, the size of this black hole is 10 microarcseconds, 100,000 times smaller than the limit of the eye. So Genzel was able to find this black hole and work on it using the same technique as the presence of little speckles in the image Laberry had found. And by selecting those images, he could show that the black hole, which is at the cross there, was surrounded by many stars. This is an image where the resolution of image is about 20 times better than the speckle limit, and crossing the speckle limit, thanks to Laberry's technique, allowed him to observe, when time passing, the images of all the stars, or many of the stars close to the black hole, to see their orbits. And once you know the orbit, then you have the size of the value of the mass of the black hole. So it led him, so you can see here the star moving around the black hole, and the time is on the top to the left. And now if you magnify it, then you go much closer to the black hole, and of course you can follow one of the stars, which is called S2, and you see the perfect ellipse that this star is making. And here is the orbit of the star, but I don't detail that. It will be in the presentation. But the most important point is that, one, we have a black hole at the center of our galaxy. Two, we know the mass of this black hole, 4 million solar masses. Three, the stars around this black hole move. Some of them go very close to it. How close? Can we see what happens? That's the next step of the story. Next step. In 1989, there was a first revolution to cross the seeing barrier and to get sharper astronomical image. This was called adaptive optics. Adaptive optics was first successful in France in 1989. I was lucky to be part of this team. And you see that the wavefront coming from the sky, they are on the, here we have the wavefront, which is deformed by the Earth's atmosphere, which is reflected by a mirror, which uses the information from the star itself to correct the wavefront. When the wavefront is in advance, like here, it will retard it by changing the shape of the mirror. When it's delayed, like here, a little bit, a few microns, several wavelengths yet, it will advance it by moving the mirror in the other direction. The result is a flat wavefront, and then this flat wavefront is used to make an image. And you see on the right the corrected image, which has even a diffraction ring, which is much smaller. And as I told you before, instead of 1 arcsecond, for a 5-meter telescope, we have now 20 times smaller diffraction circle. Therefore, much better details on the image. Adaptive optics was very preliminary at that time. We obtained, that's the first demonstration, we looked at the double star, and you see the same disk, which is very bad. And then when you turn the adaptive optics on, then you get a double star image, which is very sharp. So this is, this has been, of course, immediately installed on a number of telescopes. And today, one does not build a large telescope on Earth without adaptive optics. So I will not go into the technical details of optics, robotics, computer science, of course, to move the mirrors, which are fascinating. I just give you one example. This is an image of a star, but it's not a double star. It is a star with an exoplanet. You know probably that today we have thousands of exoplanets around other stars. This is the first image ever made of an exoplanet around, it's a big one, it's about Jupiter size, around the star, which is a brown dwarf. And the star image is very nice. You can see that it's corrected by the adaptive optics. And the distance is little less than 1 arcsecond, 0.7 arcsecond, but it's perfectly resolved. So applying adaptive optics to the study of exoplanets has become an immense domain of astronomical observation. But an additional step has been used. I told you a minute ago that to inform the moving mirror of adaptive optics, we use the a part of the image of the star itself. But to do that, the star has to be bright enough. Otherwise, in this short millisecond time, there will be not enough photons to inform the mirror. Therefore, adaptive optics wouldn't work. Well, except that if you use a clever trick, but a big one, you shoot a laser from the telescope to the sky. This light will meet a layer at about 80-kilometer altitude in our atmosphere, where there are sodium atoms which are in permanence deposited there by meteorites. So we have a thin layer, of course it's invisible to the eye, of sodium atoms sort of floating in the atmosphere. If the laser light is tuned to the resonance wavelengths of sodium, in yellow light, then it will excite those sodium atoms, which will re-radiate the same wavelength, or another wavelength actually. And if you catch this radiation with your telescope, so the laser light goes up and the radiation will come down, and if you make an image of an artificial star created at 80-kilometer altitude, now you can place this artificial star nearby your faint star you want to image with adaptive optics and use the artificial star to inform the mirror, and that works. And it works so well that you will see at the end a modern telescope which has not only one but 4 lasers coming out to make the system more flexible. So you see the combination with adaptive optics and laser stars or artificial stars gives an extremely powerful tool to beat the saying limit and to achieve the factor 20 or so, which for 5, the telescope here is an 8-meter telescope, so the limit is close to 15 milli-arcsecond. So another example, those are the 10-meter telescope of the Keck Observatory on Mauna Kea in Hawaii. And those mirrors, they are different. They are made of mosaic, but the atmosphere has the same trouble, have been equipped with adaptive optics. Here you have Andrea Ghez, who is using this telescope, and she got the Nobel Prize with Reinhard Genzel because she also studied with the same technique of sharpening the images, the black hole as the center of our galaxy. I show you also adaptive optics for the sun because it's so spectacular. This is, you see, this is an image of a sunspot obtained without adaptive optics. This is the right part of this image. And with adaptive optics. And you see the sharpening of details at the surface of the sun is really spectacular. This is the full image, of course, where you see the filaments which are driven by the magnetic field and the granulation on the surface of the sun. So much for adaptive optics. I drop that and I speak about a second revolution to see details in image. We call that optical interferometry. And 20 minutes or so I have now will be devoted to this second revolution. Where does it come from? It's a different story of adaptive optics. Adaptive optics' first idea was 1958. Optical interferometry first idea was by Hippolyte Fizeau, a French physicist and astronomer, who in the 1851 said, well, of course, we are limited in sharpness of images by the size of the telescope mirror, which is here. But maybe we can artificially increase the size of the mirror by putting 2 mirrors at several meters apart or tens of meters, use the light from the star on each of those mirrors, reflect the light of the star with 2 additional mirrors here, feed the telescope with this, have simply here two holes which correspond to this distance, and then we form the image at the focus of the telescope. And then we should have fringes, interference fringes at the focus, and this should allow us to measure the diameter of a star despite the seeing, because then we would have the resolving power not of the diameter d of the telescope, but of the distance between those two mirrors. The idea was caught by Albert Michelson, who is otherwise famous for his disprovement of the existence of ether, and he installed on Mount Wilson, on the largest existing telescope in the world, 1913, exactly the proposition of Fizeau, which you see here, one mirror here, reflecting mirrors here and here, feeding the primary mirror of the telescope, which is there, getting fringes, and measuring the first star diameter, the star Betelgeuse, 50 milliarc seconds, 20 times less than the diameter, than the seeing limit. This was a great achievement. But technically, it was quite difficult. Michelson was a genius in experimental physics, and nobody was really able to repeat his experiment until 1975, where a young Frenchman, I already spoke of Antoine Laberry, said, I do it again, but he didn't use a big mirror with two holes and distant mirrors like that. And he was able, I show you in a minute his instrument, he was able to obtain stars on the fringes on the star Vega. Of course, the measurement of this French spacing, given the distance between the two telescopes, immediately gave him, like Michelson in 1920, giving the size of the star. You have here a look at the very crude equipment. So this is a good demonstration for young students. With bright ideas and crude equipment, very not expensive at all, you can make a fundamental discovery. Here, that's telescope 1, that's telescope 2. The light is reflected in the central laboratory here. The distance is 12 meters, and you get the fringes on Vega. And you see the combination system is also very crude to make those fringes on a photocathode, which gives this image. So this was a great success, so great that in the 1980s, immediate 5 years after that, we began to dream of a large interferometer. This is a drawing that Laberry made at this time to propose to the astronomical community. Will it come? To propose that we design interferometers, because they make interference fringes, with telescopes at a large distance, and the longer the distance is, the better the details of the image are. Of course, if you use a large telescope instead of the very tiny one that Laberry used in his demonstration, then you need to correct the image for seeing, which means that in fact this dream could only work if you have adaptive optics. At that time, adaptive optics was only a dream. So we had first to develop adaptive optics in the 1980s. I showed you the final demonstration in 1989, and then we could think of a large telescope interferometer. This was achieved with the European Very Large Telescope in Chile, which was inaugurated in 1998. You see, we have 4 telescopes of 8.2 meters each. They are distributed on the surface in such a way that the distance between the two most distant is 130 meters. This gives, therefore, the possibility for the fringes, if obtained, and that needs a lot of careful optics, to go to detail which are no longer 20 milli-arc second, but a fraction of a milli-arc second. And this was successful a few years later, since in 2001, we obtained the first fringes with 2 telescopes on the VLT site. We have actually, on top of those 4 large telescopes, you could see that there are 4 small telescopes, 1.8 meter in size, which have also the interferometric capability, but in addition, they are movable. So they can be moved on those tracks like trains, and moving them gives a possibility of better image reconstruction. So it was successful. Interferometry can work, and it has been since then so productive that I cannot resist the idea to show you one example of this production. Coming back to the black hole, to study with the interferometer and the 4 telescopes the black hole, which was already measured, as I showed before, with its elliptical orbit, but at that time the error bars were quite large. The uncertainty on the position of this S2 star was quite large. Then the interferometer could give much better resolution than adaptive optics and improve this uncertainty. An instrument, a very sophisticated instrument, was constructed receiving the light from all the telescopes. You can imagine the transport of the light at an accuracy of a few nanometers from the mirror of the telescope to this recombining focus. 4 telescopes, so there are 4 inputs. In fact, there are 5. There is one additional possibility. And here is the result on the left. You can see that here is the black hole, and there is light due to the surrounding of the black hole. Here is the star, S2, which has this elliptical orbit. And here we have the 65 milli-arc second separating the two. But you see that the details are much smaller than this distance. This is because the use of optical interferometry. Now, where are we going in the future? We have now 2 revolutions. One is interferometry, one is adaptive optics. The first one I presented. The second is optical interferometry. What will be the telescopes in the optical? Optical for astronomers means visible light from blue to red, that our eyes see, but also near infrared, up to 10 microns wavelengths, where the atmosphere of the Earth is sufficiently transparent to allow ground-based telescope to work. So where are we going? Well, this is an artist's drawing. The telescope is nearly finished now, of the new European project in Chile. 39-meter mirror. Of course, it's a mosaic installed in the Atacama Desert in Chile, not far away from the Very Large Telescope, which I just showed, on a different mountain, which is called Cerro Armazones, 25 kilometers from the first site. In this site, 16 European countries have united to build this giant telescope. And here you see on this drawing, artist drawing, you see the artificial star. You see the lasers, which are, each laser projects an artificial star on this layer of sodium at 80 kilometers altitude, and you therefore have a combination of artificial stars which are around the object you study. The inauguration of this telescope, which is nearly finished now, is 2.5 years from now. And it will be, of course, very powerful because you see that with adaptive optics, you can reach the diffraction limit of a 40-meter telescope mirror, which is close to 2 milliarcseconds. What a progress, giant progress with respect to the saying limited astronomy. There were a lot of discussions. What will Europe do next after this? Will we do an even larger telescope, maybe 100 meters? That seems extremely expensive and probably technically difficult, but not impossible. Or will we do an interferometer, not with 150 meters baseline, but with kilometric baseline? Because if we have a kilometer instead of an hectometer baseline, the gain in resolution is a factor of 10. And if it's 10 kilometers, the gain in resolution is a factor of 100. So perspective of discovery are very important then. So the choice has not been made for the future European project. We will probably need partnership with other countries like United States or maybe China or other. This is, in the state of the world today, this is certainly a difficult plan to make. But to conclude on an optimist point, after all, in space, it's expensive to put a large mirror like the James Webb Space Telescope, which has a 6.4-meter mirror, which you see there on this artist drawing. Launched in 2022, it's producing an incredible wealth of images. Of course, the resolution is not as much as the 40-meter ground-based telescope equipped with adaptive optics, but still, there is no atmosphere, so there is no need for adaptive optics. And recently, among the many images of galaxies that James Webb is producing that you can see on internet, an exoplanet has been observed by James Webb. This is the first exoplanet discovered by this telescope, which will undoubtedly discover many others in the coming years. This was made again by Anne-Marie Lagrange, whom name I mentioned before, as the first image of an exoplanet 23 years ago, and collaborators, of course. The star is hidden by a mask. It's something called coronographic technique. So the light of the star, which is millions of times more powerful than the light of the planet, is blocked, and you see the planet. And the planet is 1.5 arc-second, so it's well resolved without adaptive optics. Being in space, one doesn't need adaptive optics. And next year, this planet will have moved. And the year after again. So we'll have its trajectory. And it's a very young planet, slightly comparable in mass to Saturn, and around the star, which is only 6 million years. And the interesting thing on this image is that you see that there is some material around here and here, and this material is the material from which this planet was formed, again, in less than 6 million years. So this case is absolutely remarkable to study the rapid formation of an exoplanet of the mass of Saturn around a star with a sharp image given by the James Webb telescope. So this is my conclusion for the future, very optimistic. I have tried to tell the story of the blur, this astronomy's quest for sharp image in French, and this is the English translation in the book, which details, of course, the story that I have been presenting to you. Thank you very much, and I am now open for questions.
Thank you, Professor Léna, for this extremely informative lecture. It's inspiring to see where we have come from. So it's been a long journey till what we have achieved so far, and we truly appreciate your contribution to the knowledge and the science that you have developed behind these technologies. So if I may request, if any of this participants have any questions, please put in the chat box.
Thank you.
We'll take them.
Thank you. I'm always happy to share this. Will there be some question now?
Yes, we'll see if participants have any questions. Meanwhile, my question is, so what's the philosophy and the reason behind putting those large telescope, particularly in
I
Chile?
couldn't hear you.
If you can hear me, sir.
Sorry, I didn't hear you for a minute. So
Yeah, so you mentioned that European Space Agency decided to put these large telescope in Chile, right?
yes.
What was the basis that they decided that what was that specialty of that place, Chile, where you put those large telescope?
Well, the whole story is that the larger the telescope, the more light you get. So the faintest the object you observe are, and the sharpest the images are, because the diameter is bigger. So the compromise is exactly the following. How much money can you get to make bigger and bigger? And is the industry able to build this size? So this is this compromise between the challenge for the industry and the available money, which makes the final choice. So we had initially 100 meters, then it was much too ambitious, and finally 40 meters was selected by Europe to make this telescope. This was nearly 20 years ago that the choice was made.
And why particularly Chile? Why the European
Now,
Space Agency?
of course, adaptive optics can beat the bad atmospheric effect, but it cannot beat the clouds. So you have to choose a very dry area where the sky is clear most of the night in the year. And this is only in desertic areas. There are a few places in the world which have this condition in Australia, in Namibia, and in Chile. So the three of them are in the southern hemisphere, which we wanted to be because especially of the galactic center being very high in the sky. So the conclusion for the first telescope of Europe, which was this organization, which is not the European Space Agency, as you said, but the European Southern Observatory, ESO, was to go to Chile, first with small telescopes in the 60s, and then with this final product.
Right. We have one question from Dr. Muhammad Usman. So he wanted to know, are there any instances from recent past where astronomical devices were affected by space weather? If so, are there any forecast-based devices?
Excuse me, I missed the end of the question. Are there
any instances from the recent past where astronomical devices were affected by space weather?
If we had problem with space weather, yes. What? Let me explain what is called space weather. The sun is an active star. It emits particles, which is called solar wind, essentially protons and electrons, which travel from the sun, especially from those sunspots areas. I showed one of them, and travel to the Earth, and then it creates beautiful polar auroras, but also perturbation in radio communication, and it can even damage electronic onboard satellites. So all those effects are known today, and they are called space weather. And it has happened that some satellites have been disturbed, and I believe at least one US satellite long ago completely put out of order, electronic being destroyed by those events. This is why we have monitoring of the activity of the sun with dedicated instruments to find whether there is a risk. It can be predicted a couple of days before it happens that space weather will damage electronic communication, radio communication, or even in case electric power network in countries.
Right. Many thanks, Professor Léna. So now may I invite, if there are no further questions, perhaps, and there's one more question just came in. Are ground-based telescopes affected by light pollution in Earth's atmosphere?
Absolutely. The light pollution is terrible. In cities, you cannot install even a 1 meter telescope will be very limited by the light pollution scattered by the Earth's atmosphere. This was one additional reason to go to desertic area like Chile, because there you are far away from cities and therefore less submitted to light pollution. But it's an issue, and for instance, near this very site you have on the screen now, there is a plan by the Chilean companies to build a plant to extract lithium, because this area is also rich in lithium. And of course, this plant will be a real problem for this telescope. So currently there are discussions between European bodies at ESO and the Chilean government about the future of this plan. So even in a desertic area like this one, environment can become an issue. Thank you for the question. It's really an important point for the future.
Thank you, Professor Léna. So now I'll invite Professor Sayed Kumail Tayebi, the president of the East Asia Science Foundation, for his remarks. Over to you, sir.
Okay, dear Professor Pierre Elena, very nice to meet you. Just I follow your informative presentation regarding on astronomy and the black hole just and the telescope. Of course, you have good explanation in this regard. I'm sure participants to this webinar have enjoyed for your presentation for today. Of course, you are the founder of inquiry-based science education and in partnership with LAMAP, as you are the honorary chairman of the LAMAP, and in partnership with East Science Foundation. We have a long history of collaboration in this regard, and we are very delighted just you have had again here for this webinar. Really appreciate for your informative presentation, and I'm sure anybody just enjoyed your speech today. And thank you for your webinars, and hope to have more collaboration and more presentation of yourself, hopefully in the future. And looking forward to seeing you again. Hopefully, I remember I met you in Isfahan in Iran a few years ago. And if you remember, we met each other. And right now I'm here at the second president of the Istio Science Foundation. Thank you once again, and hope to see you and hope to have more collaboration in different areas for STEM education, especially to the younger generation in this respect. Thank you very much.
Thank you very much. I think that science in this sometimes torn world, science is a way to keep people united and to be communicated to the children of our country. So let's work both on science education and the beauty of science looking at the skies.
Of course. Right, you're right. Okay, Khalil.
So thank you very much, Professor Léna, for this. We on behalf of East Asia Science Foundation and IPKI, we express our deep gratitude for sharing your knowledge and the contributions that you have made over your career lifespan. And I'm confident that this webinar would continue to benefit the current participants. Not only that, because we put it on the YouTube, and so it will be a great contribution and value addition to our repository of science lectures. And we are grateful to our partners, the participants, everyone for joining us in. And we keep on inviting, legendary scientists, revolutionists, those who have made great contributions. And we are grateful to Professor Pierre for taking his time out of a very busy schedule. Thank you very much. And so here we conclude. Thank you everyone for joining us in, and hope to see you in the upcoming Science Chronicle webinars. Have a great day. Bye-bye.
All right.